Hello and welcome to another eMathInstruction Common Core Algebra 1 lesson. My name is Kirk Weiler, and today we're going to be doing Unit 11, Lesson number 3 on Discrete Functions. I just want to remind you that if you'd like to get a hold of the worksheet and a homework that go along with this video, just click on the description underneath the video. As well, don't forget that at the top of each one of our worksheets we've got the QR code that corresponds to the video. Use a cell phone or a smart tablet and just scan that little QR code and it'll take you right to this video. Anyhow, let's talk about discrete functions. All right, there's really two types of variables in mathematics. There are continuous variables and discrete variables. These have very kind of technical definitions. They're very, very deep, so I'm going to kind of really try to boil it down for you. A continuous variable or function is one that takes on all real numbers between its extremes. Okay, a really great example of kind of a continuous thing would be to say, let's say that you started off in the morning. So let's say you started off in the morning and it was 47 degrees Fahrenheit outside. Let's say later on in the day you looked at the thermometer and you found out that it was 62 degrees Fahrenheit, right? We must go through everything in between to get between these two temperatures. In other words, we can't skip 55 degrees Fahrenheit. We can't go from 47 right up to 62. We're not going from 47 to 48 to 49 to 50. We're going from 47 to 47.1 to 47.2, and it's even more than that, right? We're going through every real number between 47 and 62. Right, discrete variables or functions, which is what we're going to concentrate on today, those are ones that can only take a variety of different, that they can only take on unconnected values. So here's a good example as well. Let's say that you were monitoring the number of people that were in a store. Maybe when the store opened up, there were 8 people inside. And then sometime later, you found out and you counted and there were 19 people. All right. You certainly don't have to go from 8 people to 19 people by hitting every real number in between. You'll never have 9.2 people. You'll never have 15.7 people, right? That's discrete. Discrete variables or functions take on values that are isolated. They aren't always connected. Again, this is a very, very deep topic, but it is one that's part of the new Common Core, and we're going to be dealing with it today with hopefully some real-life examples that will help you understand the topic. Anyway, I'm going to clear out this text, and let's jump into our first discrete example. Miranda has a lemonade stand where she is selling cups of lemonade for 50 cents a cup. Letter A says, fill out the table below for the amount of money, M, that Miranda makes as a function of the number of cups, C, that she sells. So C is the number of cups, M is the money. Obviously, if Miranda doesn't sell any cups, she's not going to make any money. Now, when she sells 1 cup, she makes a half a dollar, 50 cents, whatever. I'm gonna do it in terms of dollars. 2 cups, she makes $1. 3 cups, she makes $1.50. 4 cups, she makes $2. All right. Real simple, right? Letter B, create an equation that finds the money made, M, as a function of the number of cups, C. So what is M? Well, we'll calculate how much money we make by taking 50 cents and multiplying it by the number of cups we sell. And that's really what we did up here in the table. When we had 0 cups, 0.5 times 0 is 0. 0.5 times 1 is 0.5. 0.5 times 2 is 1.0, etc. Letter C says, explain why this is an example of a discrete function. All right, and here's the key. It's discrete because, and it's all about the x values, she doesn't sell anything but whole cups. All right. Again, she's not going to sell 1.5 cups. She's not going to sell 2 3/4 cups. And even if she did, even if she sold fractional cups, the key would be she'd still be charging you as if you had a full cup, right? Now that's really important because it has a ramification for what the graph looks like, right? 0 cups, she's making no money. 1 cup, 50 cents. 2 cups, $1. 3 cups, $1.50. 4 cups, $2, right? We're just going up by 50 cents each time. So it's easy to plot all these points. Now here comes the big whammy, though. All right? Here's what we can't do. We're done. I'm going to do it in red. We're done. All right? We do not connect these. Do not connect them with a line. Don't connect with line. How about we'll just say don't connect? That doesn't look like the word connect. Sometimes my handwriting just doesn't get the job done. Don't connect. All right. Once we connect, well, then that makes the assumption that we will sell any number of cups, even ones that are fractional, and we'll even charge money that somebody can't even pay. You know, we might end up charging $4.32.7652 cents, right? These are all unconnected points. It's discrete. All right. Letter E, how many cups of lemonade would Miranda need to sell in order to make exactly $30? This is where we can use our equation, right? We can literally ask the equation, all right, how many cups will make 0.50 times C equal to 30? That's actually pretty easy, especially if you think about it as 2 cups for $1. Then it's no great surprise when we find out that we'll need to sell 60 cups. But the last question's an important one. F says, explain why Miranda cannot make exactly $28.75. So what I'd like you to do right now is pause the video and think about that. Can you come up with an explanation? All right, let's talk about it. There's many explanations that would get the job done, many that would be really good. I'm such an algebra guy that for me, I say, well, all right, I'm gonna solve. I'm gonna figure out how many cups it'll take me to make 28.75, just like I did in the last problem. I'm gonna divide both sides by 0.50. Obviously, in the last unit, we did a lot of equation solving work, so this should be a piece of cake. And I find that it takes 57.5 cups. Well, we don't sell half cups. So we can't make 28.75. It simply wouldn't show up. It wouldn't be one of the dots. Another great way of putting it would be to say that we can make either whole dollars or half dollar amounts because it's discrete. And therefore, we won't make that $0.75 amount, that 75 cents. All right, I'm going to clear out the text, copy down what you need to. All right, here it goes. Let's move on. Okay, one thing that you want to try to get good at, or at least a little bit good at, is reading over a scenario and understanding whether it's continuous or whether it's discrete. So in this particular problem, I give you 4 scenarios, and I ask you to just simply tell me whether the function we're talking about is a continuous function or a discrete function. And a good way to think about this is to think about the inputs, the x's, if you will. Then there's no x's in this problem whatsoever. But the inputs, the independent variables, can they go from one value to another value without passing through values in between? If so, it's discrete. If not, it's continuous. Let's take a look at the first one together, and then I'll have you think about the other ones on your own. Letter A. A person who is driving at a constant speed of 62 miles per hour has a distance traveled, d, given as a function of time, t, in hours by d equals 62t. So is that continuous or discrete? And again, think about this variable, right? That represents the time you've been driving. So, there's probably a point where you've been driving for, 1 hour, and a point where you've been driving for, let's say, 2 hours. The question is, can you just skip from 1 to 2 without passing through all the times in between, or do you actually have to, exist in the space-time continuum, as the physicists would say. And you have to. You can't skip from 1 hour to 2 hours, right? So this is most certainly a continuous function. All right. Pause the video now, read through each one of the other three, and decide for yourself whether you think it's continuous or whether you think it's discrete. All right, let's go through them. Letter B. Franklin is selling candy bars to raise money for the drama club. Each candy bar costs $2.50. The money he raises, M, as a function of the number of candy bars, B, that he sells is given by this. All right. Hopefully, you said this was discrete. All right, this is very similar to our lemonade example, right? And it's discrete because B can only be whole numbers. All right? So you can sell 1 candy bar. You can sell 2 candy bars, 3 candy bars, 4 candy bars, but you can't sell pi candy bars, 3.1415, etc. You know, you can't sell 2.7654321 candy bars, right? That's why it's discrete, okay? Whole numbers of candy bars. Letter C. A teacher imposes a 1/2 multiplicative penalty each day that an assignment is turned in late. I don't know if you've experienced this before. At the high school level, oftentimes if you turn something in late, teachers will penalize you on your grade for each day that you turn it in late. And so this thing says the total credit, C, that a student can earn based on the number of days it's late is given by this. All right, where D is the number of days late. Well, even though D represents time here, it is still a discrete function. And it's a discrete function because, again, the teacher is going to penalize you if D is 1, if D is 2, if D is 3, if D is 4, etc. But the teacher's not going to be looking at their watch going, well, you turned it in after D equals 2.73543 days, right? So those inputs can only be whole numbers. They can only be, separated numbers. Let's take a look at D. A bathtub is draining at a rate of 3.2 gallons per minute from an initial volume of 164 gallons. The volume of water left in the bathtub after m minutes was given by this function, 164 minus 3.2 times m. Now this is an example of a continuous function. All right, and again, it's this simple, right? At some point in time, right, it's been draining for 1 minute. At some other point in time, it's been draining for 5 minutes. There's no way to go from there to there without passing through all times in between. 1.76532 minutes. We passed through that, right? 2.87354 minutes. We passed through that moment in time, right? That's different from letter C, where D is measuring the number of days, but that input can't be anything but a whole number of days. Here, we could certainly put in a fractional number of minutes, even an irrational number of minutes. All right? So I'm going to scrub out the screen. Pause it now if you need to. Okay, let's get rid of the text. All right. The last exercise we're going to do is going to look at, I don't want to say limitations of discrete models, but kind of like something quirky about a discrete model. Let's take a look. It says Malik is trying to compare texting plans for 2 cell phone companies. His options are given below. So option A, what's going to happen is they're going to charge Malik $12.50, always. And then on top of that, he's going to pay 2 cents per text, or $0.02. Doesn't sound terrible, pretty cheap in terms of the amount of money you gotta spend per text, that is if you aren't using some free texting service. Option B, on the other hand, you don't pay any monthly charge, but you pay more per text. All right? So it's a good example of sort of like pros and cons, right? Option A, I gotta pay that $12.50 up front, but then my texts are really cheap, 2 cents a text. On the other hand, option B, I don't have to pay anything up front, which is good, especially if I don't send many texts, but then I'm paying more per text. Letter A says, write equations that give the total monthly cost C based on the number of texts made N for both options. Pause the video now and see if you can do this for yourself. All right, let's go through it. It's pretty easy. For option A, the cost, well, we're going to start with that $12.50. There's no getting around that. No matter what, we've got $12.50. But then I have to add to it 2 cents or $0.02 times the number of texts I make. That's it. Option B, on the other hand, well, I've got none of that $12.50 going on, but I do have to pay for 5 cents times the number of texts I send. All right. Letter B says, why will Malik not be able to find a number of texts where the two plans charge an equal monthly amount? All right, well, let's actually try to figure that out. Let's set option B's cost equal to option A's cost. Right? I mean, if they're asking us why we can't do it, I say we dare them and say, well, we're gonna do it. We're gonna actually figure out the number of texts when the two plans cost the same. Just watch your arithmetic here. I know the decimals can be confusing, but 0.05 minus 0.02 is 0.03. All right, and again, you've got your calculator. And what we find when we do $12.50 divided by 0.03 is we find this, 416.6 repeated. Now let's think about that. Why is that not kosher? Why is that not okay? Because we can't have fractions of texts. Cannot have fractions of texts. It's not to say we can't have a fraction in a text, but we can't have fractional texts. We can't have 416 2/3 texts. So that's what's known as a non-viable solution to an equation. It's a solution, but it's not viable. It doesn't work. We can't use it. On the other hand, it does give us some information, right? Now, I kind of want to show you the information it gives us. Let's do something really quick. Let's say we've got 416 texts. Let's figure out using our calculators how much each plan would cost. So plan A, right, that's going to be my $12.50 plus 0.02. Let's figure out when I send 416 texts, how much that's going to be. I didn't figure this out up front. I'm winging this. That's going to be $20.82. On the other hand, plan B, well, that cost is just going to be 0.05 times 416. These should be pretty close, right? 0.05 times 416, and that's going to be $20.80. Whoops. So plan B is cheaper, just barely, right? Now, on the other hand, when we get to 417 texts, watch what happens. The cost for plan A is $12.50 times 0.02. Oh, that's weird. Let's try $12.50 plus 0.02 times 417. I don't know why I didn't just add 2 cents to the last one, but we get 20.84. On the other hand, for B, when we do 5 cents per text times 417, we get 20.85. So take a look. Originally, at 416, B was the better plan. But by 417, A becomes the better plan. So even though that 416.6 repeated isn't particularly helpful in terms of knowing when they have the same number of the same cost, well, actually it is helpful. It tells us they never have the same cost. But what it really is it's a cutoff point, right? Before 416.6 repeated, plan B is better. After 416.6, plan A is better. So it does still give us some information. All right, Why don't you pause the video now, copy down anything you need to. All right, I'm going to clear out the text. Let's finish up. So many of the functions that we work with in math are continuous functions, especially when somebody just says to you, hey, plot the equation y equals x squared. You plot points, you connect them with a smooth curve, all is good with the world. But with discrete functions, those input values can't just be any real number. Very often they're just whole numbers. Sometimes they can also be just fractions, but no irrational numbers. And we'll talk about those later on in the course. All right. So until next time, let me just remind you this has been an eMathInstruction Common Core Algebra 1 lesson. My name is Kirk Weiler, and until next time, keep thinking,